Hello everyone, welcome to a new video and here I am going to explain about priority interrupt controller. First of all, I am going to share with you something. If we are working with an 8086 microprocessor, we will face a problem here because the 8086 has only two interrupt inputs. We all know about them. One is NMI, that is non-maskable interrupt, and another is INTR. These two pins are dedicated for interrupt inputs in 8086. Okay, if we save NMI pin for a power failure interrupt, that we know it is very important, then this leaves only one interrupt input for all other applications, and that is INTR pin. For applications where we have interrupts from multiple sources, we use an external device called a priority interrupt controller to funnel the interrupt signals into a single interrupt input on the processor. In this part of the video, I am going to show how a common programmer priority interrupt controller, I mean PIC, the Intel 8259A, is connected in an 8086 system, how it is initialized, and how it is used to handle interrupts from multiple sources. Okay. To show you how an 8259A functions in an 8086 system, we first need to review how the 8086 interrupt input works, or INTR input works. If the 8086 interrupt flag or IF flag is set and INTR input receives a high signal, then what the 8086 will do? First of all, it will send out two interrupt acknowledgement pulse on its INTA. This is the interrupt acknowledgement pin. Okay, so through this pin, it will send two interrupt acknowledgement pulse to the INTA pin of 8259 program priority interrupt controller. Okay, what does that mean? 8086 has a INTA pin, and again our priority interrupt controller 8259A has also an INTA pin. So whenever the 8086 IF flag is set and interrupt will be received by INTR input, then it will send out two interrupt acknowledgement pulse from its INTA pin to the 8259 INTA pin. Okay, the INTA pulses tell 8259A to send the desired interrupt type to the 8086 through the data bus. Okay, what does that mean? That I am going to explain. Suppose 8086 receives a interrupt signal from to its INTR pin, then if it wants to service that interrupt, it will send out two INTA pin interrupt acknowledgement pin from its from 8086 INTA pin to the 8259 INTA pin, and by this pin 8086 wants to tell 8259 that please send me the desired interrupt type through the data bus. Okay, so what can be the desired interrupt type? That means type 0, type 3, type 244, type 254, okay, etc. Then in the next step, whatever the type it will get, it will multiply the type that it receives from the 8259A by 4. You know this multiplication, I have described in my previous video. It will multiply it by 4 to produce an address in the interrupt vector table. Okay, this is the example that I have described. Then these steps are also same above, that it will push the flags on the stack, it will clear interrupt flag and prep flag, then it will push the return address on the stack. This is the of the mainline program, okay, where the interrupt has been occurred. Then it will get the starting address for the interrupt procedure from the interrupt vector table and load the address in CS and IP, and from the CS and IP it will calculate the actual physical address of that interrupt service procedure. Then it will go to that procedure to serve that, and finally it will execute the interrupt service procedure. Okay, so this is how an INTR input works, but you have to remember that at first it will send two interrupt acknowledgement pulses through its INTA pin, two pulses. Okay, Now let's take a closer look how the 8259A functions during this process. This is the internal block diagram of 8259. In the figure, first notice the 8-bit data bus and control signal pins that are in the upper left corner of the diagram. Okay, this is D0 to D7. That means it is of 8 bits. This data bus allows the 8086 to send control words to the 8259A and also read a status word from 8259A. Okay, I am going to describe control words and status words later. Then there is some read-write control logic. The read and write inputs control these transfers when the device is selected by asserting its chip select input low. So this is active low signal. So whenever the chip select input is low, then it will enable the 8259A. Otherwise, it will be disabled. Okay. The 8-bit data bus allows the 8259A to send interrupt types to the 8086. Okay, I have described about interrupt types: type 1, type 3, type 244, etc. So this data bus will help 8259A to send to 8086 the type interrupts and their other procedures. Then observe that in the right corner there are the 8 interrupt inputs labeled as IR0 through IR7. These are the 8 interrupt inputs on the right side of the diagram. If the 8259A is properly enabled, obviously by selecting the CS pin, an interrupt signal applied to any one of these inputs will cause the 8259A to assert its INT output pin high. Okay, suppose in IR0, these are the 8 signal lines or 8 pins that and interrupt comes through these pins. Okay, suppose I have connected a keyboard through, and if that wants to send any interrupt, it will send it through IR0. Again, I have connected a mouse. If that wants to send any kind of interrupt, it will send by IR4. It's depend on my desire. Okay, again, if I connected a monitor, then it will send any kind of it. If it wants to send any kind of interrupt, then it will send by IR3, etc. So whenever any of the interrupts come through these 8 pins, then the INT output pin will be high. If and this pin is connected to the INTR pin of an 8086. Look, this figure. This is 8259 and this is an 8086. Okay, this INT pin is connected to the INTR, that means pin number 18 of the 8086. And if now the 8086 interrupt flag is set, then this high signal will cause the previously described INTR response. Okay, if the INTR or if the interrupt flag is not set, that means 8086 was not ready to receive any kind of interrupt. Then this interrupt will be disabled. Okay, or you can say this interrupt cannot be serviced, or maybe serviced later, not now. Okay, but if this pin is the IF flag is set, then it will receive that interrupt and served by I have described by these procedures. Okay. The INTA input of the 8259A is connected to the INTA output, INTA output of the 8086. The 8259A uses the first INTA pulse. You know, there will be 2 pulses. The 8259A uses the first INTA pulse from the 8086 to do some activities that depend on the mode in which it is programmed. When it receives the second interrupt acknowledgement pulse from the 8086, the 8259A outputs an interrupt type on the 8-bit data bus. Okay, so interrupt type I have described later. The in case of first interrupt acknowledgement pin, it will set itself whatever the configuration we have used or we have sent through the 8086, and in the second INTA pulse, it will send 8086 that type of interrupt through this data bus. The interrupt type that is sent to the 8086 is determined by the IR input that received an interrupt signal and by a number you send the 8259A when you initialize it. The point here is that 8259A funnels interrupt signals from up to 8 different sources. 8 different sources mean from keyboard, from mouse, from printer, from scanner, etc. Into the 8086 interrupt input. And it says the 8086 is specified interrupt type for each of the 8 interrupt inputs. At this point, the question that may occur to you is what happens if interrupt signals appear at, for example, IR2 and IR4 at the same time? What will happen then? In the fixed priority mode, the 8259A is usually operated in. The answer to this question is quite simple. In this mode, IR0 input has the highest priority, the IR1 input the second highest priority, IR3 input the IR2 input the third highest priority, and goes on, so that the IR7 input has the lowest priority. What this means is that if two interrupt signals occur at the same time, the 8259A will service the one interrupt with the highest priority first, assuming that both inputs are unmasked. What is unmasked mean? Mean enabled, okay? Assuming that both inputs are enabled in the 8259A. In the block diagram, note that the 4 boxes labeled interrupt request register, interrupt mask register, interrupt service register, and interrupt service register and priority resolver. Okay, then now I'm going to describe about these registers in short. The first one is interrupt mask register. What is the purpose of it? It is used to disable or mask. We know what is masking. Masking means disabling. Okay, it is used to disable or enable. Enable means unmask. Disable or enable individual interrupt inputs. Each bit in the register corresponds to the interrupt input with the same number. Okay, look at this figure. This is interrupt mask register IMR, and these are the IR0 to IR7. These are the 8 interrupts. Okay. Now, if you want to unmask or enable an interrupt input by sending a command word with a 0 in the bit position that corresponds to the input. Okay. Suppose if we want to unmask anything, in this case, okay, look at this figure. This is the register, 8-bit register. Here 0 means this is unmasked or this is enabled. That means IR7 interrupt is enabled, IR6 interrupt is enabled, IR1 interrupt is enabled or unmasked. But if we want to mask any interrupt, that means if we want to disable any interrupt, then we have to put 1 to that interrupt pin. Okay, suppose this is the IR4 pin, and if we want to disable IR4, if we want to disable IR2, in this case we have to use 1 in to mask these interrupts. Okay, so in this figure we can easily understand that IR7 is enabled, IR6 is enabled, but IR4 interrupt is disabled. That means this pin is somewhat disabled, that it will not take any interrupt request from the connected device with the pin IR4. Okay. Now another register is interrupt request register. It keeps track of which interrupt inputs are asking for service. Okay. Look, connected IR0 to IR7 is connected through these registers. Okay. If an interrupt input has an interrupt signal on it, then the corresponding bit in the interrupt request register will be set. Suppose this is the interrupt request register IRR. If let's assume that there is an interrupt request comes through IR4 pin, okay, then this will be set, and there is no interrupt in other pins. Okay, suppose a keyboard is connected this IR4 pin, and it wants to send attention of CPU. It wants to interrupt CPU, interrupt 8086 processor, right? So this in this pin, device wants service or wants to interrupt. So this pin will be set. If any kind of interrupt comes through IR2 pin, then it will be set. I mean, there is the value of 1. Okay. An interrupt signal must remain high on an IR input. This is IR input until after the falling edge of the first interrupt A pulse. Okay, if IR4 is set, then it will INT pin will be high. It will send to the INTR pin. Then from the INTA pin of 8086, there will be 2 pulses. So it will have to be set 1 until it will get the pulses. Okay. Now there is another register, that is in-service register. It keeps track of which interrupt inputs are currently being serviced. For each input that is currently being serviced, the corresponding bit will be set in the in-service register. This is in-service register. Suppose I have explained before that keyboard has interrupted. Keyboard needs attention from CPU, and it will send an interrupt signal. And if the 8255 is servicing this interrupt, then ISR will keep track of that the interrupt 4 is being serviced. Okay, so this is set 1. This actually keeps track of which interrupt is being serviced. Okay,